Hello, welcome to Lecture 17. In this lecture, we're going to carry on with our discussion of electric potential energy. Let's do a conceptual energy example. What we have here is a couple of capacitors where the upper plate is positive and the lower plate is negative. This creates an electric field in the capacitor which points from positive to negative or straight down. We're going to release a positive charge from the midpoint of one capacitor. We're going to release a negative charge from the midpoint of the other capacitor, and then we'll ask some questions. Okay, question A. What's the direction of the force on each charge? By force, we mean the electric force, because charges in an electric field feel an electric force. And the electric force is the charge times the electric field. And our charge here is allowed to be positive or negative. If our charge is positive, which is what we have in our left picture, then the force and the electric field point in the same direction. So in this case, our electric force points down because our electric field points down. For our second charge, our negative charge, force is still charge times electric field, but if E is down and Q is negative, it means our force is going to point up. So our electric force on our negative charge points straight up. There's our Fe, and our electric field E points down. Okay, that's part A done. Part B, which way does each charge move? Well, they're each released from rest. The initial velocity is 0, so each charge will have an acceleration, that's force divided by mass. If the force points down, the acceleration is down. If the force points up, the acceleration is up. So if they start from rest, they're going to move in the same direction as the acceleration. So the positive charge moves down in the direction of the force. If you push it down, it's going to move down. Our negative charge, we push it up, it's going to move up. Okay, B is done. Part C. Okay, here's where we're getting into the work and energy stuff. What is the sign of the work done by each charge, work done on each charge by the electric field, okay, via the electric force? So here we have to remember that work is equal to force dotted with the displacement, delta R or delta Y as you see fit. So that's the same as the electric force times delta R times the cosine of the angle between the force and the displacement vector. So why don't we go ahead and draw the displacement vectors? So for our positive charge, we said it moves down. That means delta R is down. For our negative charge, we said it moves up. That means our delta R points up. Okay, so what's the angle between the force and the displacement for our positive charge? Well, force is down, displacement is down. The angle between those two vectors is 0. So for our positive charge, theta equals 0. Work is positive. For our negative charge, displacement's up, force is up. The angle between those two things is 0, so the work is going to be positive. So theta equals 0, work is positive. Okay, C is done. Does the electric potential energy of each charge increase or decrease? There are a few different ways to think about this. If you're an equation kind of person, you might remember that delta U is minus the work done. So if this was your cup of tea for your thought, the change in potential energy is negative of the work. If the work is positive, and it is positive in both cases, it means delta U is negative. If delta U is negative, it decreases. So in both cases, delta U equals minus work. Delta U is negative, therefore U decreases. Okay, same argument over here for our negative charge. Delta U equals minus work means delta U is negative, which means U decreases. That is a perfectly valid line of thought and an argument. If you didn't care for that thought, you might remember the expression that U equals the charge, whatever the charge is, times E times Y. Y here is your distance relative to the negative plate. So our positive charge moves closer to the negative plate, which means y gets smaller because we choose y equals 0 at the negative plate. So for our positive charge, we go from some positive y value, that gives us a positive potential energy, to a place where y equals 0, that gives us a potential energy of 0. So our potential energy goes from a positive value to 0. That means it decreases. Okay, so that's a reasonable explanation as well. Another explanation is it speeds up as it goes towards the negative plate, which means that the kinetic energy increases. If the kinetic energy increases, then the potential energy has to decrease. Okay, so those are all good arguments. Okay, for our negative charge, the arguments are the same. So our initial potential energy is going to be a charge, a negative number, times the electric field, times a y value. And our y value is about a medium size. It's 0 at the negative plate, it's medium in the middle, it's big at the top. Our negative charge starts with a medium-sized negative value of u, and it moves up to the top plate. At the top plate, y is bigger, so we get a bigger negative potential energy. So we go from a medium negative potential energy, say minus 50 joules, to a big negative potential energy, say minus 100 joules. That means our u value actually decreases because minus 100 is smaller than minus 50. So that's a legitimate way to think about it. You could also think that if our work is positive and our charge is moving with the force, it's speeding up, so the kinetic energy gets bigger. If kinetic gets bigger, then potential gets smaller. For a homework example, I'm going to say that we have an electric field that has a magnitude of 20,000 newtons per coulomb, and it points towards the left. It's between the plates of a parallel plate capacitor, and the spacing of that capacitor is 1 millimeter. We release an electron from rest at the negative plate and we let it move. So it's going to move towards the positive plate. We know electrons are repelled by a negative and attracted to a positive. So the electron is going to move from negative to positive. The question we have to answer is, what is the electron's speed when it reaches the positive plate? Now, there are actually two ways you could do this problem. You could use kinematics. You know your electric field, so you could find your electric force. Once you know the force, you can find the acceleration. Once you know the acceleration and the distance, you can find the final speed. In general, that's a legitimate way to do this problem, but since we're in the energy chapter, I'm going to suggest that you do this problem using conservation of energy. So figure out how much energy does the electron have at this plate, how much energy does the electron have at this plate. You know those two energies have to be the same, and see if you can use that to find the speed when it reaches the positive plate. For this example, we have a proton and it's shot towards the positive plate of a parallel plate capacitor with a 0.5 millimeter spacing. So the space between these two plates is a half of a millimeter. The electric field strength is 500,000 newtons per coulomb from positive towards the negative. If the proton is projected from the negative plate with a speed of 2 times 10 to the 5 meters per second, does it get to the positive plate? If it does, what's its speed when it gets there? And if it doesn't, how close does it come? So if we think about what happens, our proton starts right here. So here is our proton. It has a positive charge, and it goes with some initial velocity vi, which is 2 times 10 to the 5 meters per second. So it's going to start to move towards the positive plate because we've thrown it towards the positive plate, but we know it's attracted to the negative and it's repelled by the positive, so it's going to slow down as it approaches. This is not different than throwing a ball up in the air. It slows down as it gets towards the ceiling or the highest point. Okay, does the proton reach the positive plate? So what's our strategy going to be here? Well, why don't we go ahead and recognize that we know the initial velocity, we know something about the electric field, so we can analyze this motion. Let's use some physics and let's decide how far does it go before it comes to a complete stop, and that's where the velocity is 0. If that distance is less than a half a millimeter, then no, it doesn't reach the positive plate. If it's equal to a half a millimeter or bigger, then yeah, it does reach the positive plate. Okay, so there's our strategy. Let's see how far it travels as it comes to a stop. We could use kinematics here, but since we're in an energy chapter, let's use energy methods. Let's start by writing down our expression for conservation of energy. So our final mechanical energy is our initial mechanical energy plus work done by non-conservative forces. We don't have any friction or anything, so the work done is equal to 0. Let's make sure we understand what final and initial are. So final is where it comes to a stop. We don't exactly know where that is. It could be right here, it could be right here, or it could conceivably go further. So we don't know where it is. We're trying to sort that out. Initial is where it starts. We know that value pretty well. It starts over by the negative plate. So by final mechanical energy, we mean the final kinetic plus the final electric potential. And by initial energy, we mean the initial kinetic plus the initial electric potential energy. Okay, so let's see what we're going to put in for each of these terms. I could fill it in all underneath here, but it's going to get a bit crowded, so I'm just going to move off to the side for these calculations. So final kinetic energy is 1/2 times the mass times the final velocity squared. Now remember, final is where it stops. That velocity is 0 because it stops. Final electric potential energy is the charge Q times the electric field times the final distance. We don't know what this final distance is, but if we wish, we can go ahead and label something in our picture. So let's say it gets to here. And at this point, we might remember that we choose our y-axis relative to the negative plate. So this is y equals 0, and positive y is towards the positive plate. Okay, so what do we have next? Initial kinetic energy. And I could fill in my values for charge and electric field here, but I don't think I'll do that just yet because it'll get a little bit full. So initial kinetic energy equals 1/2 times the mass times the initial velocity squared. So that's 1/2 times the mass, that's given 1.67 times 10 to the minus 27 kilograms. That's the mass of a proton. We multiply that by the initial velocity of 2 times 10 to the 5 meters per second. Don't forget to square that. It's easy to make algebraic mistakes. What we get for that value is 3.34 times 10 to the minus 17 joules. That's a very small energy. And that makes sense because our proton is very small. It has a big velocity, but it has a very tiny mass, so it has a very tiny amount of energy. Our initial potential energy is the charge times the electric field times the initial position. The initial position is at the negative plate. That's where y equals 0. So our initial electric potential energy is equal to 0. Okay, now we have something to fill in for every term. Let's go back over to our equation. Kf is 0. UEF is the charge times the electric field times YF. YF is what we're trying to find. That equals to K initial, 3.34 times 10 to the minus 17 joules. And if you were a symbols kind of person, you could have left that as 1/2 times m times vi squared and filled it in later, plus UEI, which we found was 0. So then YF is equal to 3.34 times 10 to the minus 17 joules divided by Q times E. Q is the charge of a proton. That's 1.6 times 10 to the minus 19 coulombs. It's also divided by E, which was given as 500,000 newtons per coulomb. Okay, pop that through the calculator, and what you should get for your distance is 4.175 times 10 to the minus 4 meters. Now our plate separation is given in millimeters. Why don't we write this in millimeters as well? So YF is 0.4175 millimeters. Okay, so the answer to our question, does it reach the positive plate? Well, our proton comes to a complete stop after it travels 0.4175 millimeters, sorry. So our proton leaves the negative plate, it slows. When it gets here, it hits 0. So no, it doesn't get to the positive plate. It comes this far, and then in fact what happens is it's going to turn around and come back because it's attracted to that negative plate. So it gets this far, it comes to a complete stop. So let's write down the answer to our question, does it reach? That would be a big no. Okay, so our follow-up question, if it doesn't reach, how close does it come? Well, how close it comes is this distance right here, delta y. So we're trying to sort out what is delta y because that's how close it gets. This slide is a little full, so I think I'll do that calculation on the next slide. So let's just add our plate separation to our diagram. We know that the total distance between the two plates is 0.5000 millimeters. We know that the proton comes to a complete stop after it has traveled 0.4175 millimeters. That means delta y, how close it comes, is going to be 0.5 minus 0.4175. Delta y, so to answer our question, how close does it come? Delta y is 0.5 millimeters, and you can do this in meters if you prefer, it doesn't matter. 0.4175 millimeters. And that gives us an answer of 0.0825 millimeters. Some interesting twists you could put on this question would be how fast would you have to project it in order to get it to just reach? You might also layer in a little bit of kinematics. You could ask how long does it take to get to that distance? And then how long would it take to get back to its original position? So there are lots of different little twists we could put on this question.